So next we have Austin Roche. He's a software architect here at Maplesoft, and Austin will show us some Maple tools for numerical analysis. So welcome, Austin.
Thank you, Kashka. Yeah, so today I'm going to present the student numerical analysis sub-package in Maple. I'm just showing right now the help page. Let me just make that smaller. There we go. Yeah, so there's a brief description here, and you can see there's a large number of commands. These are is basically designed to help students in an introductory numerical analysis course. So you can see a large number of commands here. And if you go on, so these are divided into the visualization. There's some interactive commands like tutors, and there's a large number of computation commands as well.
Austin, sorry to interrupt you. There's a request. Could you zoom, please? Zoom in because the text is a little small.
Can't really zoom into a help page.
Yeah.
Yeah, sorry, I can't really zoom into a help page. I'm not sure how to do that, but this is not.
You could save it as you could put it in, save it as a worksheet and then zoom. Maybe that might work. I mean, just click the icon on the top, the save as a worksheet.
I don't know which one this one.
Yeah, yes.
No, that's not it.
Yeah. Okay. Yeah, don't worry about it. We'll
yeah, I can just copy the whole page and then put it in a worksheet. Hold on. I do this. No, it's not what I wanted. I'm not sure it works. Okay. There should be a open page as a worksheet. There we go. Yeah, sorry, this wasn't super. No, that's not what I wanted. Okay, anyway.
People can zoom directly in Zoom. They can zoom in, so maybe we'll just move on to the...
I think we should move on. The help page is not super important. I mean, you can look at it yourself. I just wanted to introduce the package that way. There's a secondary glossary page that's linked from that help, and it kind of divides the various commands into interpolation. So there's two main commands in interpolation. There's polynomial interpolation and cubic spline. Those are two different ways of doing interpolants. One is obviously polynomial and the other is connected cubics that match the slopes at the connection points. And then there's a large number of things that you can do with these kind of internal data structures. And then there's also some quadrature commands that do approximate integrals and some root finding commands and then a large number of numerical linear algebra commands and some initial value problem commands. And then there's some more general tools, just finding absolute errors and checking the number of significant digits and relative error and rate of convergence and Taylor polynomials. So I'm now going to go to now hopefully everyone can see this better. Just a number of examples. So first of all, to start, I'll just press restart, and then you can load the package using with student numerical analysis, and you can see a large number of commands that you can use that way. I'll just hide that output. And here's some initial value problems. You can see what you can do. So here's a simple linear differential equation. Sorry, not linear. And you can find the value at t equals 4, given this initial condition, y is 0 equals 0. And there's certain methods that you can apply, and just in this case, we've asked for output equals solution. In this case, it's the same thing, but ask for the possible error value as well. So it's correct within a value of 2.002. And then it can also produce a plot if you ask for output equals plot, and you can see the blue curve is a high quality numerical solution, and then the red curve is a Runge-Kutta fourth order approximation. And you can try the compare with option, and it does a number of different types of approximations here. And this one outputs the information in a table. So this is Maple's numerical solution, and then different, this is a Runge-Kutta fourth order, and then the error terms and the Euler approximation and some error terms for that, and the fifth order Taylor approximation and the error terms for that. So I'm going to move on into interpolation. So suppose we have some data, and we want to approximate this by a polynomial. So we use a polynomial interpolation command. In theory, the exact function that this data is supposed to be representing is this function that we can give it here. These are not very good approximations to that functions, as we will see. And so we can ask for the interpolating polynomial from this data structure. The polyinterp, this is an internal data structure, and it gives kind of a polynomial approximation. You can see each term has factors, which are the x value minus the value of the data point, the x value of the data point. And the coefficients are determined by trying to match these the y values as closely as possible. And then we can ask, for example, what's the approximate value of this this interpolating polynomial at a given x value, x equals 6, and it will give this answer. And we say, well, hold on, well, I've got another data point just showed up, and it's actually the value that I want at say 6.003 is going to be 9. And so we can add that and it'll give us a new, more kind of accurate interpolation. And then to compare, we can draw the first object, and you can see it was going down at the end. So when you got to the value on x equals 6, it would probably be down here somewhere. And indeed, that was represented by this value minus 3.7. But when we added the new point, it changed the polynomial interpolant, and now it's going up, and that more closely interpolates the kind of the data that we have. And we can also draw the basis functions. This is a series of better and better approximations. So you have the the constant term, then the linear, the constant approximation, the linear approximation, and then a quadratic approximation, then a cubic, I think is this one, and then finally you've got a quartic here. So those are a sequence of better and better approximations to the data that you have. And again, you can ask for certain properties of that interpolant. For example, the function, this is supposed to represent the exact function, and the remainder term, that's based on the difference between the interpolant that you have and the exact function for various values. So this would be the values c between these two numbers. And for example, you could also ask for a cubic spline. It's a different kind of an interpolant. Sorry, I didn't show the output there. So this is just a similar, it's also stored as a internal representation. And you can draw that and you can see this is a quite accurate, it's nice, it's a smooth curve and it's a bit less, it doesn't have the same, it's actually hard to see the difference there, but it's supposed to be a little less jumpy, basically. So moving on, let me know if there's any questions in the meantime. You can also do a bunch of numerical linear algebra operations. So given this matrix, we can do a PLU decomposition as follows. And we can do stuff like check the properties of the matrix. Is the matrix shape strictly diagonally dominant? And it says true. And then, for example, if we want to use it, if we set up a system, so we have that matrix as our coefficient matrix, and we have this vector as the vector values, we can try to solve mx equals v, and using various different methods that are available, we can get an answer this way. And then we can also, there's a number of commands for doing numerical quadrature. So for example, if we have this function f equals sine of x, we can do, this is the integrand, I believe, for doing the approximate approximation to the, I think the arc length, if I'm not mistaken. So, and then if we want to numerically approximate the value of that integral, we can use this quadrature function. So we can also use the output equals plot, and it shows you what it's doing internally. So it's got these, it's plotting the function, and then it's using these red kind of equally spaced values, x values, finding out where they hit the curve, and then using those as approximations for the height of the curve, and getting an approximation for the integral that way. And so this is using a different method, Newton-Cotes, instead of this method up here was Boole. And in this case, we've given a different option for the output. We've output the information. So the information table, so it's basically showing a bunch of information here. I'm not I don't fully understand all of this information, what the status means. But yeah, it's just a bunch of information on that particular method for doing adaptive quadrature. And then moving on, root finding. So this is, say you're given this function, and if you want to do find the roots where this function has the value 0, what's the x value? So you would, and you're looking from x between 0 and 1, it'll find this value 0.6022. And for example, we can change the method to the Newton method and then output a plot, and it shows you that it starts over here and it follows the tangent down to this down to the x-axis, and then uses that as the new x value and follows the tangent back up, and so on and so forth, and there ends up at this point P5. And yeah, I will just continue now if there's no further questions on that.
1
There's a
minute.
number of tutors. So for example, actually 4 tutors. So interactive formula tutor, you click on that, you can input some matrices. I think it comes with these defaults, and so you can edit the matrix, change the numbers in here. So if I want to change this 10 to 11 to 10 over here, and you can edit the vectors, the coefficient vector, and so forth. And then you can change the method for solving and the number of iterations and so forth. You press compute, and it'll give you an LUD decomposition, and then use those matrices to put them in the formula and give you the output that results from that for the solution. And when you're done with that, it outputs a bunch of your data that you used. Secondly, the Euler tutor. This is for solving initial value problems. So you have an ODE, initial condition, and say you want the value at the endpoint t equals 3. Specify the number of steps, the number of digits, and then you can choose to return the plot or just the solution. If I press display, I'm sure that changed anything. What's changing is down at the bottom. So this will give you a command that you can use. Yeah. Okay. And then the initial value problem tutor. This is very similar to the last one, the Euler tutor, again, for finding initial values, for solving initial value problems. We'll just close that. And the matrix decomposition tutor. Say you have this matrix and you just want to do a decomposition. There, just press that button. Of course, you can edit the matrix beforehand. And I'll just close that, and it outputs the different values of the LUD decomposition.